Hello everyone, how are you today? Good. My name is Michał. I work at Reality Games here in Krakow, where we are building games based on big data. And today I want to talk about how are we doing that, what kind of techniques are we using in order to create and maintain services used by our games. I will be showing techniques in Scala and functional programming, but before we start, and while we are waiting for for other people to join, I'd like to tell you a functional programming joke. Why did the chicken cross the road? That's the question. I don't know why. It's very simple, really. The best way to understand it comes from the idea of contravariant functor. As you probably know, a functor is just a mapping between categories that respects the category structure, a homomorphism, if you will. Now, some constructions that we want to express look like functors, but in some sense turn morphisms around. We call these contravariant functors. As you probably noticed, we can indeed define a contravariant functor as simply a covariant functor on opposite categories, invoking the obvious correspondence. Of course, you have already noticed that the obvious connection this has with the category theoretic, and so on and so forth. So this has been a very popular joke recently, and I really like it because it makes perfect point. We as functional programmers want to teach and show examples of functional programming based on theory, based on this kind of explanation you've seen about why did the chicken cross the road. And this talk is a different one. People like to learn from examples, and that's why we should be focusing on examples. Theory can come next or not at all in some cases. So this is a controversial one, but should be something you can lean on and while you're learning about the functional programming concept. So this talk is divided in two parts, fast and functional. Functional part is where we will be building a real-world Scala microservice, a service, which will be very modular. So we'll be able to plug and play different components inside the service and achieve something because of that. And the second part is fast and functional. So fast has two meanings. First one is the objective of the talk is that we'll be talking about performance. So I'll be showing you as a nice addition. You are all JVM developers, so this is like a JVM-wide technique. Flame graphs. So this is something that we can really we can use to understand our service performance. And the second meaning is if it's very modular, very isolated and separated, the things inside the service, we can have a better development speed. This is what we are using in our company to develop services. So this is something that we are really trying to preach about. So again, fast and functional, flame graphs performance, simple real-world Scala service. And the example that we'll be using, I'd like to have like examples that are very practical, that can be useful, and but still fit one presentation, one talk. So this is what I came up with. Marketing tool. So you know that if your company is producing a new product, you want to market it. And in all days, you had billboards and TV commercials, so it was an easy task, right? You have a new product, you need to buy some time on TV or buy some billboard. And nowadays, it's kind of more difficult. So you need to tap into social media, right? You need to buy the influencers' time. So the influencers are the people on YouTube or Twitter or Instagram that have many, many followers. And you as a company can just go approach them and ask them about, okay, can you put our product or mention our product in your video or in your Twitter or in your Instagram post, right? And then as a marketing people, you'd like to have a holistic view of the campaign. So this is the service that we want to build. We will be basing it on YouTube. So a collection of videos that are from different influencers about the same product is a collection, right? And you'd like to have statistics of all the videos. If you have 5 videos, then you need to fetch everything from about those individual videos and then present to the user the aggregated value of views and likes and so on and so forth. So very, very simple business feature, but still pretty useful if you want to keep video or post statistics. So this is what we'll be doing, what we'll be creating. This is a collection of, this will have collection of videos, ability to store the collection with particular list of IDs, and the functionality should also kind of calculate, based on this video list, how many total likes and views the collection has. So three requirements. First one, ability to store the collection. So collection of product X is video from YouTube #1, video #2, and then this particular identifier. That's all, right? So you just keep them in storage. Second requirement, for each individual video, you need to fetch the current statistics through the YouTube API, right? And of course, you need to be able to calculate stats. If you have statistics for particular videos, you just need to aggregate them. So very simple business logic. And of course, you need some kind of non-functional requirements. You need to have a HTTP server, you need to have collection storage in memory or in the database, whatever. You need to have some kind of logging or metrics, right? This is an example of some cross-cutting concerns. And in functional programming world, we like to divide our applications in two worlds. The first one, the blue one, this pure world. When all you have is pure functions. Pure function is the function that just calculates its output value based solely on the arguments, doesn't do anything more. Those kind of functions are easy to test, easy to reason about, because you don't have anything more to worry about if you are looking at the implementation of the pure function. And the second, over the fence, you have this side effect, the impure world. When you have functions that do something more than just calculate value based on the arguments, like HTTP calls, logging, getting something from the database, and so on and so forth. So we need to keep this kind of division in our brains in order to have a better chance at maintaining the code. And from the requirements I've shown you, if we want to divide them, this is something that we come up with. So the calculate stats, the function that gets the videos, statistics, current statistics of particular videos, and calculates the sum of likes and views and so on. This is a simple, pure function. Only arguments are taken into account when you're producing a value. On the other hand, on the other side of this fence, we have all the others, right? Saving collections, fetching collections. We have this YouTube API fetching ability, HTTP calls, right? Server, client, logging, collection storage, all those things are side effecty. So they can really blow up our application if they want to. And our ultimate goal is to move as many things from this red side to the blue side. This is the thing that we want to achieve. But why? Why do we want to achieve that? There are three main reasons, and lots of other ones that are derived from them. We want to test in isolation, because we want to have stable tests. We want to reason in isolation. As I said, if you have a function that only is concerned about arguments, you can really think about what it's doing without taking into consideration any environmental things. And of course, we can easily swap components, which is the thing that we'll be using in our plug and play later on. And this is the agenda for this talk. So we are, after the introduction, you know the example, we are around here, so the less hardcore thing. And now, as a warning, I'm showing you this kind of slide, because I will be showing the Scala code that we are using in our company. And I know that it may be a little bit difficult to comprehend for some of you. I want to highlight the signatures. What kind of signatures are we using? I'm showing all the code just for having a big picture. And one more comment, we have like Python developers joining our team that are doing this kind of functional programming in Scala. So they are just switching from the dynamic to static, and they are very productive. So I think, and we think, that this kind of technique that I'm showing is really is not really for just advanced programmers. It can be used by anybody. That's why I want to show and highlight this thing. After the code will smooth out and calm down, and I will show you those flame graphs and performance tests for JVM wide purpose. Okay, modular programming using algebras. Model. Who of you has some Scala experience? Scala experience, Kotlin experience. All right, like I don't know, 20% of the room. So this is how we define data classes in Scala. So this is basically the collection is just a class which is immutable, doesn't have any setters, and has this list of videos that you need to provide when you're constructing it. And it's always available, it's immutable, you can just pass it around or copy to a different instance, but that's all. So we'll be using something like that to model our domain. So collection of videos is named collection and has a list of video IDs from YouTube. Influencer item can be a YouTube, a video can be a Twitter a tweet or Instagram post, right? We'll be focusing on YouTube, but influencer item is a generic definition of those things. And collection stats is ultimately what we want to our service to produce at the end. So all the one collection, what kind of stats does it have currently? And I was talking about pure functions, right? So calculate is the only pure function, the only thing that was on the blue side of the wall, of the fence. So this is a function that gets list of influencer items like YouTube videos and produces a collection stats, right? Again, collection stats is impressions, engagement, score, so the holistic statistics of this particular collection. So we can really have this kind of pure function right here. So this is a pure logic. This is what we'd like to have everywhere, but this is the only one we have so far. So this is how would we implement it in Scala. Fold left is something you have in Java 8 streams as a reduce. So this is like reducing a list into one particular value, and we are just we are creating collection stats step by step by going through each element of the list and adding engagements, views, comments, and so on and so forth. Doesn't really matter. This is just a business logic. What matters again is its signature, right? It gets a list of influencer items, and after the colon, you can see it returns collection stats. Nothing else matters. We can just focus on this signature, and we understand what's inside. We don't really need to look at the implementation. We don't really need to look at fold left or reduce or something like that. We just can see from this signature that it's calculating the collection stats based on list of influencer items. So pure win, it's easy to reason about. We don't have to deep dive into the code. Can it be as easy as the previous one when we want to create a function that is the whole service, like get collection results, and you just provide collection ID? And what do you need to do in order to implement that? You would need to get the collection with this ID from some kind of storage. You'd need to get the videos out of it. You need to, for each video ID, you need to call the YouTube API, and then finally calculate the pure function we just implemented. Now, of course, you need some logging in between. Okay, so you need to add some logs. So there are some impure side-effecty things as we go on through the functionality of the whole service. So nope, we can't really do this as a pure function. In Java, we have something like Computable Future, right? So this is the same service. It's also implemented in Java. So this is how it would look like when we want to have asynchronicity, right? We want to call the YouTube API, YouTube video APIs for particular video in parallel because they are not dependent on each other. So this is something that we'd use, right? Asynchronous Computable Future API. This is the beginning of the Java implementation. So we are getting the collection, then we are composing it with another fetch video statistics function, and so on and so forth. So we are doing something like that. So this is something that we also have in Scala. It's called Future. It's exactly doing the same thing semantically, just asynchronous, multiple threads. The values will be available in the future. You can have some kind of parallelism and things like that. And on pure functional way, we have I/O, which is very similar to Future. It's more functional friendly, but it doesn't matter for this presentation. What matters is it's really similar in what it can do with the Computable Future from Java, which is what you are accustomed to. And what's the problem between I/O future and computable future? It's one big problem that really makes our work, our job as developers harder. They are too powerful. When you look at this code, right? You look at the signature, get statistics based on collection ID. It returns collection stats. But what it also does inside is like this send human to Mars. If you have function that can return computable future, the implementer of this function can do anything, can spawn a new thread, can do heavy lifting things, can save something to database, get something from the database, and just by looking at signature, you can't really figure it out. You need to go deep into the implementation, possibly many classes down deep the stack in order to understand what's really happening, right? So this is just an example. And in Scala, there is this, Scala and soon in Kotlin, there is this language feature I want to talk about just briefly to introduce you to this feature. It's called higher-counted types. And it allows us to do this kind of thing. So we can have this effect f, which doesn't do anything, and the f is chosen by the user. Okay? So we have asynchronous, synchronous, and then we have this IO effect type future, completable future, and then we have this f type. What does it mean? And I want to tap into your intuitions by comparing this type to generics from Java. So when you look at this Java code, this function f, what signature, what it can do, how many implementations can you come up with? Just shout out. Sorry? Infinite? Why do you think so? What's one of the infinite possibilities then? Sorry?
You could replace A with string.
No, but as the implementer of this function, function. So just implementation of this function. This is what I'm talking about. So the user of this function chooses string or int, right? But as an implementer of this function, f, you can't choose. A doesn't do anything. You can't really use the functionality of A inside the implementation of function f. Okay? Right? What you can do is you can use the list. So you can just get first element, second element, third. So the number of possibilities is just the number of elements of list. You cannot do new A. You cannot create a new A. You can't even add first and second element because A doesn't have plus operation, right? So all you can do, you can just return elements from the list. So this is how constrained you are as an implementer of this function. It's very good. We want to use the same thing. This is a non-compiling as you see Java code. We want to have a similar thing, but on a higher level of types. So we'd like to replace the future with f. We'd like the user to choose the type of f when they call it. But inside the function we are using, we just want to focus on the business logic. We don't want to focus about threads and any like parallelism. Is it the future, asynchronous, synchronous? We don't want to do it. So f doesn't do anything, it's chosen by the user. So this is kind of thing that we can have in Scala and soon in Kotlin, higher-counted types. So we can just, after the colon, provide the functionalities that this f needs to have in order for our function to be compiled. But other than that, if you don't have anything after the colon, it doesn't do anything. So in order to have like sequence operations, first that, then that, then that, we need to have this monad functionality. But that's one thing. But then we need to have this collection view. This is our code. Collection view functionality, and this helps us, again, just look at the signature. We are just building the signature, and as a user of the signature, you will choose the effect type. But before that, in the signature, you can see what this function can do. It cannot send humans to Mars. So collection view, you can fetch a collection using type f. It can be synchronous, asynchronous, IO, future, completable future, whatever you want it to be, your user want it to be. So you don't have to choose here. And the collection view looks like that. So again, this is something that returns, trait in Scala is like interface. So it's just interface with one method, which is called fetch collection returns f. The same with the video client. Video client is HTTP client to fetch some things from YouTube. Again, very similar thing. We are just adding this functionality as a constraint to our type f, and then we can use it inside the function. So when you look at the signature, you can see that it's f needs to be monad, collection view, and video client in order for this function to be compiled. And of course, this looks very similar. The trait looks very similar to the one that we've seen before. So it's just one method and returns f. So effect, no matter what. And there's this function calculate, which we implemented, the pure one, which can be used because it doesn't use anything from f, right? We don't have to add any more constraints to our signature. And of course, we need to have some logging. So when you see that the code looks, it's done on purpose, we added a lot of logs into it so that we can analyze the performance of this functionality easier in presentation mode. But when you look at it, it looks very, very similar. Again, the logging is just a trait, so one interface with one method, message string, and returns f from unit. Unit is void, so nothing happens, right? So it returns a value that is just singleton value, nothing more is conveyed. So this is the whole service. This is the whole service. By looking at the signature, you can see what's happening, what can happen inside. This is the service that we won't touch again. So it's all implemented and it's all done. Again, the signature is the most important one. So f is a very, very constrained type, which we adding more things into it as we need them. So we don't have computable future, which can do anything. So signature is enough in order to understand it. And what we did is we really moved lots of things from side effecty things into pure world, because algebras, when you look at them, they return f. They don't have any spawning thread possibility. They don't have anything like that. They don't have any side effects. And algebras and interpreters are pure and side effecty kind of things. The algebras are the pure implementations, like the f, nothing more, just f, no matter what. And interpreters need to choose the computable future or I/O or something like that in order to implement the real functionality, right? Because you really need threads in order to call YouTube API. And just as an example how the interpreter looks, it's just one slide of code. This is what matters. As you can see, instead of f, video response, this one highlighted, you have I/O of video response. That's what really ticks here. Interpreter is just one module, one small file, and everything in this application is just one small file. So now we are here. So you've seen some Scala code, and you've seen some constrained type f, which can be a future, can be an I/O. We call it effect type. So this is something that we use a lot because we have some flexibility around that. We can have some flexibility around that, and we can do things like plug and play. So what I did for this presentation is I implemented some interpreters for those algebras on the left. So for video client, I implemented Akka HTTP is one of the server clients HTTP, most popular client in Scala ecosystem. I use a second interpreter, Apache, standard Apache thing, using Hammock, and HTTP4S is another client that we can use. So 3 different interpreters, 3 different clients for HTTP. When you're looking at these examples, think about your Java application, whether you can really have different HTTP client implementation in your application. The same with linked list for the collection view. Collection storage is ID to video IDs. And logging, I also implemented 2 interpreters for logging. The first one is log all, so everything is logged to the console. And second logger is just something that will drop logs when the rate is higher than 1K per sec. So the why is we'll want to make it fast. This is the performance kind of test. But that I will be doing on the laptop. Please do not perform those things on production. I'm just showing it as a development mode. You can have like order of magnitude improvement of your service on your local laptop, and this technique is pretty useful in those early days of the service. We'll use WRK. This is a normal like Linux Unix tool. I don't know if you're familiar with it. Somebody? Not many. Free people. So this is normally downloaded as a package, no matter what kind of distribution you use. WRK will be using this command line, this command in command line. What it does, it uses one thread, 16 connections, and over 30-second duration, it dumps as many requests on our service URL as possible. Dash dash latency means that we want to have the report for the latency. And I will show you how it works in a bit. And so WRK will be used to put some load under our service, right? And Async Profiler, again, this JVM tool, pretty new one, will be using in order to profile, to sample what CPU is doing inside our service. In this case, -D10 means over the 10-second period. And what Async Profiler will do, it will produce a flame graph. Flame graph, who's familiar with flame graphs, use them? Cool, okay. So I will do a short introduction how to use them. You are reading from the bottom, and I will generate one, and we'll go through it to let you know how to read them and what kind of information can we get out of the flame graph. So the version 1 of the application, the one that I've just shown you, this is the business logic. This was the business logic, and now it's time to test it out. So see what kind of behavior does it present. Let me know if you see what's happening. The right side is the most important one. So the highlighted one. This is the application that is running, and I'm doing this kind of test by adding 1,000 collections to have like some data in it. And then when you see, I'm using the WRK in order to run the 30 seconds test. And on the second side, I'm just getting the process ID from the Java process and profile it using the async profiler, right? So async profiler now samples what's happening in our application, and WRK are putting a lot of load on the application. So after the test's finished, WRK will show us the report, and the async profiler will show us the flame graph that's been produced. So the report looks like that. So you can see that we got 8,000 requests, right, in 30 seconds duration, which amounted in 273 requests per second. And we have this dash latency. 99th percentile is 119 milliseconds. And the YouTube API here is Dockerized on my laptop, so it's okay. It's something, right? It works. And maximum that the peak was 371. So that's how it works. And yeah, 850. 82 milliseconds, something around that. And how the flame graph that is being generated here, was being generated here, looks like. So it looks like that. This is an SVG file that was generated by Async Profiler about what kind of performance our service had. So you have this one graphical representation of the performance under load of your service. And no matter how big is your service, you can still have some information inside it. So you read it from the bottom. And at the bottom, you don't really need to see it, but it contains all the samples that were generated. 2,000 samples were gotten from the CPU, and the sample is just a stack. So the async profiler goes into the application 2,000 times in 10 seconds and checks what CPU is doing. So what's the stack trace? What's the stack trace? What's the stack trace? And then gathers the same stack traces in one bars. So when you look at that, you can see that the thread, fork join worker thread, was in 85% of samples. And you go up, and you can see that there's this HTTP server, which was in 46% of samples. You are going up, and you are looking for your package, for your code, right? And yeah, here it is. So you can see that 55% of samples, 55% of samples contained on their stack trace contained this logging info thing. So our service bottleneck is this logging implementation we have, because most of the time, more than 50% of time, it's logging something. And when you look at this, when you look at this code here at the bottom, I will make it bigger. Here at the bottom, you can see some other colors than green. So Async Profiler generates green bars for your application, including the libraries, and other colors for system calls. And you can see that you have some also system calls inside it. So what you can do is you can also check whether, for example, just-in-time compiler was running, and then your performance tests weren't so good. So this is something that you can also use to really test the real performance of your service, instead of what you think. So when I run this several times, this is one of the times it got like 70% of time in the flame graph was on the logging method. And now the cool part of the architecture comes into play, because what we can do, we need to change the logging infrastructure, right? What we can do is we can change just one line of code. This is what this type F gives us, really. This is what it gives us, because our implementations use F. They don't really know how all those things are implemented. So we can just change one line of code, and here, from default logger, which is like one of the interpreters, and we can change it to a new dropping logger, which drops if the rate is higher than 1k seconds. So it looks like that. So as you can see, another small module just does its thing. It isn't concerned with anything more. And here's our function that is served. This is the function that we implemented, right? So it looks still the same. We don't have to change it at all. So it logs something, but we don't have to change it. And after that, when we run something, a change like this, when we run something like that, we get order of magnitude improvement. So we get 89,000 requests just by changing one line of code, because all the modules, including the non-functional one in our application, are totally separated, are totally isolated from each other. And the 99% latency is also better, so 62 milliseconds, so on so forth, 3,000 requests per second, pretty good. And of course, each test is like 30 seconds plus minus some time to set it up, but it's a small amount of time. And we can generate another flame graph and see that the bottleneck right here is in our fetch video list response. So the call to YouTube API, right? 20% of samples were met when the async profiler sampled our code in 10 seconds. So 2 seconds of CPU time were more or less used to call the YouTube API. So what we need to do, we need to change the HTTP client, right? We just changed the HTTP client. Again, one line of code is changed, because that's how it works, just as I did with the logger. And we get another improvement, a small one, but still an improvement. The 99% latency is the best one. So it's kind of where we are going at, right? One line is changed, and we can just test a totally different setup. And if we look at the flame graph, we get this Hammock HTTP client as a bottleneck 50% of time. So we can see that we can't really get rid of this HTTP calls, because our service, let's be honest, is just calling the YouTube API most of the time, right? So what we need to do, in order to improve the performance, we need to add caching. And we can add caching without changing the logic. Without changing the implementation I've shown you with the F-type, we can just add caching as another layer inside the interpreters, not inside our business code, which can be totally isolated, totally tested in a totally different way. And we can just add caching in the same way, just by adding one line of code, changing one line of code. And we get another order of magnitude improvement, like 933,000 requests in 30 seconds duration on these laptops. It's like 31,000 requests per second. The 99% latency is not better, but you know, there is a trade-off between latency and throughput. So we got a very, very huge throughput. So latency is not as good as it used to be, but still okay-ish, right, for this kind of application. It's up to you, to be honest. And then there's this flame graph. There's this flat surface, the top, bottom down. When you look at it, it's called sun, misc, unsafe. That means that when the async profiler got into our application, and 30% of the time or 40% of the time, the CPU was not doing anything, waiting for the I/O to end. So we could just finish right here, right? We got like 31,000 requests per second, so it's a lot. But because we have this kind of architecture, and we can just have like 5 minutes test, we can change something else. We can just replace the whole server. You know, the HTTP server that is used by our application implementation, with one line of code change, and we just replace the ACK HTTP with HTTP4S, so another library, without changing the business logic, without changing anything that we've written so far, just changing one line of code, changing the interpreter, and we can have 1 million requests in 30 seconds, right? For this particular application, doesn't mean that HTTPS is better than ACK HTTP in general. It just means that for this particular application, under this particular case, load, it's behaving better. So we got almost 40,000 requests per second for this small service that does real HTTP calls. And there's this flame graph, which of course we could go and analyze and see another bottleneck and play with that. It's up to you. It's up to developer and the team whether you want to pursue more performance out of the service. But this is where we stop during this presentation. So this is another flame graph generated from Async Profiler. And before we go into conclusions, I'd like to talk about inventions that already exist. So there's this thing called PostPod. It's like two years ago. A normal Silicon Valley startup, what they did is they marketed something like you can bring your own piece, the space when you can meditate or relax with you, and you can just have it with you in all times, and you know, create it here over here whenever you really want to relax or meditate or do something like that. So this is a real product that was marketed, right? And of course, sarcastic as it is, the internet reacted, right? This is a tent. You invented a tent. So this is the first invention that didn't really exist. But Silicon Valley is Silicon Valley, right? And the second one, out of 3 I want to show you, is this Lyft shuttle, cheaper taxi that drives on fixed routes. So the Lyft drives on the fixed route, and you can hop in and hop out whenever you want. You have a schedule. So what did they invent? It's like 1 year ago. Sorry? Bus, right? They invented the bus. So they really invented the bus. And of course, the internet reacted in the same way. And the third invention that doesn't exist is algebras in interpreters that I show you, right? So you can have like many different small interfaces, and then can be used in one function. So what's that, in your opinion? What did we invent in Scala and functional programming? Sorry? Interface, right? Interface and implementation, right? Something like that. You could argue that it's the same. So why do we use this instead of old, useful, well-tested, and pretty old, 20-year-old or 20-year-old in Java, right? Interface and implementations. I want to quickly talk about the one major difference, so that you can go out from this talk and have this kind of feeling of what's possible with higher kind of types, which is not possible without them. So this is the Scala FP implementation with the F type I've shown you, and this is the Java one, which is also in GitHub. Does the same thing, exactly the same thing, but uses Computable Future. And this is the main difference, because when you look at these interfaces and algebras used F, and interfaces need to choose the effect type. They need to really say, when you're doing this the interface creation, you need to say what kind of type will it return, what kind of effect will it be inside, right? So this is Computable Future. You need to choose something like that. And of course, the difference in usage is that if your function returns Computable Future, it can do anything. It's way too powerful, and you need to go into implementations, and you don't really have the separation of concerns and isolation. So it's too powerful for normal usage. And algebras use F, so they really don't make you use any effect type. So you as a user still have power in order to choose the effect type you want, and the implementer of the functionality is constrained to all those things inside the signature, nothing more. No sending people to Mars or anything like that. And the second minor thing is dependencies, right? In Java, you'd need to have this kind of constructor dependencies or injection or whatever. But here you can see them in the signature. You can see exactly what's happening in the signature, and those things are still not making you use Computable Future. So not an interface. There is a major difference between them. We can abstract over the effect type, abstract over the Computable Future, and make our implementations constrained, which are smaller and less dependent on the outside world. So that's the main benefit of this approach and main takeaway from this talk. So what have we done? Changed the infrastructure details, but without changing our core logic. This is done in exactly the same way. When we are implementing real features, you're just doing the business logic, and you don't care about the effects until the end, until you really want to create the whole application, not just the pieces of it. So modularity, separation of concerns, all those old school things, this is what we are pursuing. We can replace server implementation, state implementation, logging, and HTTP client, anything like that, without changing anything in core logic or tests, because they are very highly separated, thanks to this F-type, hierarchy type. So a pure win. And of course, we have a lot more things on the left side, on the pure side, and we can use unit tests on the pure side, which are stable, which are very quick, and very constrained using this F-type, because we can, in tests, we can choose not Computable Future, but just synchronous sequence. So it's easier to test. And the interpreters need of course the future of I/O, or there are no constraints, so they can do anything they want. They are very powerful, so we need to integrate test them. And it's very important for me to say it. So there's just 2 slides about test containers. Do you know test containers? Do you use it? Not many people, but this is Java library, very cool Java library, which helps you create Dockerized things inside your test automatically. They just provide the port of the service. We are using it very heavily. So this is, again, 1 slide of code. This is the whole integration test of 1 interpreter. So whether it really fetches things from the YouTube or not. So it's not end-to-end integration test. It's just 1 small module that is tested. And we have integration tests for interpreters and unit tests for connection between them. So it's all tested with a lot of coverage. So I really recommend using them. So what we did is a fast and functional service. It's very fast, 38,000 requests per second. And we were able to optimize it because we used flame graphs. And the Scala service were just 1 slide of code, really, the business logic of it, and small pieces of code for the HTTP server, for the cache, for the logging implementation. So very easy to test and very easy to reason about, because there are small isolated pieces of code. This is the GitHub repository that you can use. In order to learn more about that, I will show you this repository here, because all the steps I've taken are really nicely explained here, so step by step. You also have this Java code that we can see and comment about. So all the flame graphs are generated there, SVG files. So without generating them on your computer, you can just look at this repository and play around with them and see whether they can be okay for you. And as I said, they can be used in any Java program, any Java process. So you can really learn a lot by having those things. WRK is also explained here. So everything in this repository, including the Scala and Java code. I really recommend you to have a look at that. And that's all from my side. I appreciate you coming to my talk, and enjoy the rest of the conference. Thank you. So do we have any questions on Slido? How does it work? Okay. First one, have you tried perfmap agent instead of async profiler? Yes, I tried. It's a lot more. It was like 2 years ago. It's more work to set it up. Async Profiler it works out of the box. You just clone the GitHub repository and it works on Mac, on Linux, so it's a lot easier. I don't know if I answered. Please shout out if not. Another question, how does changing an interpreter differ from using interfaces and their implementations in Java? So as I said, the one major difference is that interfaces need you to choose the type of the effect, so the computable future in case of Java or anything like that. And algebras and interpreters don't really need this kind of thing. And the third question, can we use completion state instead of computable future? Yes. Yes, of course. That's the whole point, right? We can use anything we want if we are using this kind of hierarchy F type instead of interfaces which make us use this particular type. Yeah. Any more questions? Just shout it out or catch me up in the hallway. I'm here until the end of the conference tomorrow. So if you want to look around, see the code, or ask more questions about flame graphs or functional programming, just let me know. Thanks a lot again.